I have, to start this out, we're going to do our last topic of the quarter. Sadly, looking at the calendar, I don't think we'll be able to get the unit exam in this quarter. So that will have to go like the first thing on fourth quarter. I know, yes! Oh. We should still have time for the final proficiency, which will be on the topic of power. So grab your notes, start your new section on power. Today's date is 3/15. To start us out, I want a reminder though, because this has a lot to do with work, a term that we had previously. Who can remind me, what did work mean? Yes, Caitlin.
The act of adding or removing energy from an object.
It's the act of adding or removing energy from an object. And we're going to tweak that a little bit. That's a very good place to start. We're going to focus on what happens to that energy. So if I have an object and I do work on it, how might I change the energy of this? I could give it kinetic, which would mean what? It moves. So I did work and gave it kinetic energy. What other kind of energy could I give it? Gravitational potential, doing what? If I drop it, I wouldn't be doing the work, but gravity would be. Hold it up. That would be adding some energy that I would be doing work on it. What else?
You can set it on fire.
What would that do?
Thermal energy.
That would change its thermal energy in some way. It might not have the thermal energy, it might be given off. So that would be changing its chemical energy, though, into thermal energy of other things, including the bits of it. That would be doing work. How could I add thermal energy to it? Probably not, only because this is a good insulator, the rubber and stuff, so I probably couldn't do that. But how could I add thermal? What's it? That would, so I'd be giving up some of the energy through friction to that. I could even just hold it like this or like that and add thermal energy to it. All of those are examples of doing work on it. And so it is adding or removing energy from this object in all of those cases, but it's really important to remember going through all of this that that's not destroying the energy or creating new energy, right? It's just taking energy from one thing and putting it into another. Usually, in those examples, it was taking energy from me, putting it into the ball. So the definition we're going to use for work is going to revolve around that act of adding or removing energy, but it's really a transfer of energy. So work is how much energy is transferred into or out of an object. And we're going to relate this to power. We had several different ways to describe that: gravitational potential, kinetic, thermal, and we will be reviewing those, which will be a really nice review for the end of our chapter too. But for right now, this is enough. Let's please then open to page 126. We're going to read a couple pages. Would anyone like to volunteer to start reading? Maddie, go ahead.
126.
Yeah.
Think again about the energy that your body extracts from food every day. You probably get enough energy from air in one day to jump nearly 10 kilometers into the air. If this is true, then why can't you do this? You might have enough energy, but you don't have enough power. Power is the rate at which energy is converted. Power can be found using the following equation.
We'll get back to this equation, but that highlighted bold word there, power, looks like a really, really good one to define. So let's write that down because we're going to be working with it a lot. Power is the rate at which energy is converted, but we just said converting energy is work. So I'm going to change that definition just a tiny bit to reflect that this definition that we just had, that power is the rate work is done. And we've got that formula there, and it says power. Now it said it was using energy, we're going to use work. Power is work over the amount of time it takes. And if we read on and just look, it says power is measured in watts. Watts should be capitalized. It isn't in your text, but it should be. And it's abbreviated with a capital W. Why is that capital? It's a proper name. Named after James Watt, an American inventor. Here is the work done. What do we measure work in? Joules. Also capitalized for James Prescott Joule. And T, of course, is the time it takes. What's our base unit for time? Yeah. Abbreviated lowercase s. We'll do some examples, although we won't be reading a ton today. I'll try and make up for that with having lots of math questions.
Oh, great.
Thank you. Good. Yes. Would you like to choose who's next, Maddie? I'll use the die. Caitlin.
Power is measured in 1 joule per second. A 13-watt light bulb transforms 13 joules of electrical energy into radiant energy each second. A typical person can develop a power of only about 500 watts per jump. This results in a jump that is less than 1 meter high for a person with average mass.
Okay. The relationship there is kind of what we wrote up here, but it might be worth rewriting that. 1 watt is equal to 1 joule per second, just to keep that in our minds. So when we've got a 60-watt light bulb, which is the old standard of incandescent light bulbs, that would change 60 joules of electrical energy into heat and light every second. And now this one, the 13-watt, that's probably a newer LED bulb. It only uses about a quarter of the power, so it reduces by a lot the amount that is turned into light and heat. But it's really releasing the same amount of light, it's just not releasing heat like a standard bulb does, or an incandescent. Would you like to choose who's going next? 20. McKenna, please.
Energy conversions in your body. You transfer energy from your surroundings to your body when you eat. The chemical potential energy of the food supplies the cells in your body with the food that they need to function. Energy from food is often measured in calories.
Okay. Do you like to choose who's next?
You have probably seen descriptions of calories per serving on food packages, such as the size of cereal boxes or milk cartons. 1 calorie is equal to about 4,000 joules.
Just going to finish it up for us.
Every gram of fat in a food,
You are.
in a food supplies a person with about 10 calories, 40,000 joules of energy. Carbohydrates and proteins each supply about 5 calories, 20,000 joules of energy per gram. Everything that your body does require energy. The number of calories that you need for different activities depends on your weight, your body type, and your degree of physical activity. Table 1 shows the amount of energy needed to do various activities.
Okay, so table 1 there shows even sleeping takes about a fair bit of energy, about 56 watts for a medium-sized person. What is that doing? What is your body doing during that time? You've got breathing. What else? Digesting usually. Heart's beating, we need that to keep going. Brain's always working. Brains take a ton of energy for most of us. Not all.
I get the joke.
Yeah.
Give me a name.
What other thing does our body always do that takes lots of energy? Not toss and roll. What's that? Healing. Healing does.
Breathing.
Breathing we got, but it does take energy. There's one other thing that I notice a lot when I get up at night. Well, I stopped growing a long time ago, but I still maintain body temperature. That's where a lot of our energy goes, just to keep us warm. We're usually a lot warmer than our environment, and that takes a ton of energy. But we can kind of see some of the differences here. Even sitting burns about 84 calories per, calories per hour. If we have a 2,000 calorie diet, that's about 84 calories per hour. So just sitting would do that. However, we're Americans, so we often go over that 2,000 calories. And we like to do less than sitting. That might be sitting straight up even. If we're lounging, that'd be less. Maybe we're lazy enough to stop breathing for a while. We've all done that. But being more active, playing tennis, 420 calories for an hour, thereabout. Smaller people burn less. Why? Not as much body fat, but lower to the ground. There's just less mass to move, so it takes less energy to move it in a similar manner. But obviously smaller people often eat a little less too. I mean, bigger bodies need more food. That's how it goes. Let's take a look at the example problem there. I promise in just a moment we too will do some math. But here we've got an example problem that is just I don't want to do one this simple is why I don't want to do this one, but it says you transform 950 joules of chemical energy into mechanical energy to push a sofa. If it took you 5 seconds to move the sofa, what was your power? So just identify the amount of work done or energy transferred, which was 950 joules, divide by the time. So in this case, 950 joules by 5 seconds gives you 190 watts. Well, and it says a typical human can develop a power of 400 to 1,000 watts for short periods of time. Athletes are going to be able to do more than that. I would judge a lot of people could do more than 1,000, at least for short periods of time.
Like when in the homework, will you always give us?
No. That would indeed be easy. So let's actually do a few examples of things like that you might also see in the homework. Yes, in the homework you will see a question or so that is pretty very, very straightforward like that. But let's do some examples of some that are a little less straightforward, because we didn't define work that simply in our previous homeworks. We're going to review all of those ways to define work in this homework too. Starting with, let's say you lift a 1.5 kilogram book upwards by 2 meters. And it takes 1.5 seconds. How much power do you exert, I guess is the right word? Exerted, applied might be a good word. So whenever you're faced with a problem like this, you want to say, okay, how can I describe the amount of work done? What kind of energy is changing about the book in this case? Kinetic would, of course, but we can't describe it based on here, but we can describe how much the gravitational potential is changing. It gives us no real indication of how fast it's moving at any point, so that makes it tough.
Don't you just take multiply 2 and 1.5 and then times that by 9.8?
No. Yes, but let's write it out. I forgot that I had two 1.5s up there. Let's write it out so that everyone can see it. So the work in this case is going to be gravitational potential energy. Because it's how much does this change, it's really the change in that. Remember that we can always describe this delta by taking the second value of GPE minus the first value. And GPE is, what was the formula for GPE? mgh. Yep, so if we want the second value, it would be the mass times the acceleration of gravity times the second height minus mass times gravity, acceleration of gravity times the first height. We can also simplify that a little bit using our mad math skills. How can we make that calculation a little simpler for us? Perhaps by factoring. Do we have the same factors in both terms? We have an mg in both terms, right? How can we factor that out and rewrite it? Right. If we were to remove the mg of both of these, we can't change the values, but we can remove both mg. If we take mg away from this, what do we have left? H2. If we take mg away, we have, all right, minus H1. But then if we distributed this, multiplied it back, we'd get right back to this. This is kind of a handy way to do it because it says, oh, it really only matters how much the height changes when I'm doing work. It doesn't matter how much energy it had at the beginning or how much energy it had at the end. This is just describing how much it changed. And that is a little easier way to then calculate our work. We know the mass is 1.5 kilograms. Acceleration of gravity is always 9.8 meters per second squared. And the height change was 2 meters. I don't know where it started, I don't know where it ended. But it changed by 2 meters. And that's really all that matters for work.
Yeah.
That's recorded. Bryce. Now everyone knows who did it.
Well, I guess you can hear it over and over. What happened?
That would, somebody help me out, that would be 29.4. What units? Joules, because we're finding a work. We are looking for power. So all we have to do once we find work is divide it by the time in seconds. Equals 19.6. What units? Joules per second, but it's watts. Yep. We abbreviate that as watts, capital W. The computer won't be expecting it, so just use watts. Again, the Schoology isn't smart enough to know that those mean the same thing. Who's an athlete here?
Well, I'd like to get that.
Right. McKenna, do you know how much you can press? Bench press? Lift anything. Lift anything. I'm looking for I'm looking for someone who knows how much they can lift at some point in the weight room. 75, okay. 75 pounds is 34 kilograms. So let's say that if you bench press 34 kilograms by moving it the bar from, let's see, if you're on a bench, you're probably about, let's call it 0.9 meters above the ground. To, it's maybe 1.5 meters above the ground, or above the floor. Let's see, you want to do it kind of slow. Say it takes 1.2 seconds. What's your power? Power output would be a good way to put it. Complete this one with a person sitting next to you.
I'm good between there. Because 1.5 minus 0.9 is how much your height changes.
Yeah, because that's the problem. Because once you finish that one, you get the work, so you just put it.
Yes.
What would you do since you have two distances? Like a foot?
So what did the 2 meters here mean?
It's just above, up by the 2 meters.
That's what, yeah, it's how much it changed. So we had the H2 minus H1. So we do the same sort of thing here, the H2 minus H1. So how much did it change in height is the important thing.
I don't know, but I'll figure it out.
But we can. So if you started at 0.9 meters and you went to 1.5 meters, what's the change between that, from that to that? 6 meters?
0.6.
0.6 meters. That's your change in height. So that's what you'd use. Yep. Does that answer your question too?
Yes?
That one? That 1.2 seconds, not 1.5.
Not 1.5. Wait, so this one?
Yep.
Oh, whoops.
Okay, so I saw a lot of people working out. Very similar question. We know work is a change in GPE. We know that that's mg times a change in height. The mass was given as 34 kilograms. We know g is always 9.8 meters per second squared. We know the change in height here goes from 0.9 to 1.5 meters. So we could write it out, 1.5 meters minus 0.9 meters. It is equal to 0.6. And so the work done would be 166.6. What units?
Oh, joules. I put that in.
Keep all, when you're working, especially for the computer, keep all of the decimal places here because it will get confused otherwise. You can round at the
That's
end.
the final answer. That's the final answer.
Thank you. What's the energy?
199.92.
Okay, thank you. And then that work
We did it right. We did it right. Oh, we did it right. Oh, gosh.
over the time of, what did I say, 1.2 seconds?
Yeah.
That's equal
166.6.
Oops, 166.
0.6.
Let's do another. I promised you lots of math, so I will give it to you. Who plays baseball? Anybody? Any pitchers?
I pitch
Pitch some. How fast can you pitch, Jack? Do you know?
like 30 miles per hour.
I bet it's faster than that, but maybe 60-ish.
Probably about
Not even close.
No.
63.
Hunter says about 96. No,
96. Let's call it 60.
I think it's like 60. I think you pitch.
60 is a pretty standard speed for this level.
I'd say 60.
So a pitcher, let's just call him Jack.
Jack.
Throws at 60 miles an hour, something like 27 meters per second, let's call it. Ooh, I don't know what the mass of a baseball is. I need to.
Who's got a baseball?
Nuts. No, I got a softball. Yeah, it's a fair bit lighter though. I could Google it. Somebody Google it for me. What's the mass of a baseball?
Nobody else on the phone. Baseball.
There's a muscle.
Half of you guys have your phones out anyway. Give me that mass.
Small ass. What's the mass of a baseball?
That's not true. Answer.
5 to 5.5.
I get 145 grams when I Google it. That's easier for us to use.
148.8.
We do want it in kilograms, which would be how much?
Wait, what was number 20?
145 divided by 1,000. There was the baseball mass. I don't care. And the throwing motion. It's going to be pretty fast. Takes 0.37 seconds. What is Jack's power? I think, Jack, if you ever change your name, you should consider the last name of Power. That would be outstanding. Jack Power.
What is Jack's power? Invisibility.
Not being noticed by girls. Oh, that was a good one. What kind of energy is involved in this? Kinetic. So start thinking of oh, Bryce got it too. Okay, this is a kinetic energy problem. Flip back to kinetic energy. Remind yourselves.
1/2 mv squared.
It is. Sorry, Jack. Low-hanging fruit. Too easy. Oh, they'll chuckle about it. It will bring you closer together. Believe me.
Hi, Jack.
See? See? It's working already.
Velocity would be 0.7
What's that?
The velocity would be 0.7 seconds, right?
What do we measure velocity in?
Meters.
Not in meters. That would be a length. Meters per second is a speed or velocity.
Wait, so we do the kinetic energy problem?
Yeah. Yep, because that's another form of work. We're just adding energy in the form of kinetic energy.
So that looks like a turtle.
Kinetic energy equals 1/2.
I was actually made for this problem.
Your notebook's upside down.
5
I was, I wasn't enjoying the light. It was getting too hot.
times
I'll do it.
27 meters per second.
Yeah, eventually.
But there's an S, so that's what you divided it by, right? This one down here, 0.27.
We'll get there, yeah. But that's the last part, right? That's the work divided by the time.
Hey, I need to follow.
Hey,
Thanks.
what do you keep forgetting right there?
Squid. Hey, Nick, I need to follow.
How are you doing?
We didn't do it.
Why not? Kinetic energy is important too.
Yeah, I got it.
You're the refrigerator.
Divided the 5.32.
How?
You put them into the kinetic energy. Once
That's
the kinetic
what I
energy,
did.
you put it into.
Is it 142?
142.8, yes.
Okay, good. You got the kinetic energy. That equals the whatever it is.
Yep.
The
So
work. Put that back
yeah.
into your equation.
So kinetic energy is just another way to say work. But now, if you have work, how do you find power?
Now would I take 52.8 divided by 3? Where is it? 0.7?
Yeah, 3.7 I think is what I had.
So you do
It's pretty funny, wasn't it? I'm still chuckling about it. What do we need help with?
everything.
What kind of energy is Jack adding to the baseball?
Kinetic energy.
How do we calculate how much kinetic energy he added?
Isn't it the thingy times the here?
It's
I
a
got
half.
It's right here.
It is right there.
No, I flipped right to it. Kinetic energy. It's the 1/2 times and we do the second times 2.
Yeah. Yep. 1/2 mv squared.
Yeah.
Yeah. Do that. Do that.
Okay. 1/2.
And that's how much work is done because work is just a type of energy added.
I don't know how to do this. Like at all.
Do you remember kinetic energy, the formula for kinetic energy, or can you look back in that part of your notes? Okay. Part of the reason for doing this now is that it's also a good review for us for those calculations. Work and energy. I like that part. Work and energy.
Kinetic energy.
Yeah, kinetic. Right there.
Okay.
So there's kinetic energy. That's a form of work. When we do work when Jack does work on the baseball, he's adding kinetic energy. So you can figure out how much he added by using this formula.
Okay.
Because we know the mass and we know the speed, and you square that.
Okay.
Then that's the work portion. We can turn that into power how?
By dividing it by the seconds.
Bingo. What?
It'd be funny if they were
Blogging? Don't do that. But it will be on. This will be available on YouTube later.
Oh yeah.
What's it under?
I don't edit much.
What's it under? What's the?
If you go to Schoology and look at each unit has video lectures.
Oh.
Yeah, so like if you miss a day,
Oh, that makes
you click on this. I have not done this lecture before, so that's part of the reason I'm recording this one.
Yeah. Will you edit my ugly face out?
No, but I was zoomed in then.
Will you edit out that conversation?
No, that's too much work.
You're a science
Teacher, and that's
Nope.
too much work. You're trying to take over the world.
Yeah, I can just upload this and then I'm practically done. And then I can go back to lounging. Okay, ladies and gentlemen, back to our focus. When Jack pitches, he is doing work on the ball by adding kinetic energy. So we can describe that, guys. So work can also be the change in kinetic energy. So it would be the kinetic energy after, so the second one, 1/2 mv2 squared minus whatever kinetic energy it had in the beginning. But the baseball is basically still at the very beginning of the throw, so how much kinetic energy would it have? They'd have 0 at that time. So in this case, we can just say that that one is 0. and just find out how much kinetic energy did it have at the end. So the work would be 1/2. The mass of the baseball was 0.145 kilograms. Its speed was 27, and square that, which gives us how much kinetic energy?
52.8525. I was
52.8525.
52.
And then you divide it by 0.37.
Got units on that?
Units per second. Oh, kills, same thing.
Keep the extra digits. Normally I wouldn't have you do that, but Schoology is not smart enough to not do it, so we keep them. Power is that work.
Divided by 3.
Divided by 3.7.
0.37, right?
0.37.
Seconds.
142.8.
142.844594.
143 we'll call it. Probably round to the nearest one. What units? Watts. If we had something that was, say, speeding up over time, but it already had a speed, we couldn't cross this one out. We'd have to keep it in there. So we'd figure out the second kinetic energy minus the first kinetic energy. If you wanted to do the same trick, before we can factor out the 1/2 m, but this is dicey. You can't just subtract the two speeds because we still have a v2 squared minus a v1 squared. That is not the same as v2. Guys, stop talking. That's not the same as v2 minus v1 squared. That won't work. So if you were to do it, it's probably easiest to remember just to do it the full way. Find the kinetic energy after the change, the kinetic energy before the change, and find the distance. Tomorrow we will talk about how thermal energy fits into this, and talk about how electrical energy, which will be a new topic, fits in as well. A little more reading, a lot more math tomorrow.